we have seen that what we were doing actually, we were using the pipeline topic inside packet switching. Okay, so the main advantage of packet switching is that you can divide the communication a message into various packets and send the packets across the network. Okay, so what's the advantage of packet switching is that around when you are sending message from one sender to a particular telephone exchange, there will be a functionality of store and forward. Okay, so the incoming station or the station where your message has been sent can store the message for a particular duration and can send according to whenever it feels free, or whenever the resources are free, it can send the message. Okay, so the advantage of this approach is that the communication became so much easy, and there is no manual interference, and as well as the privacy is still intact. Okay, so the time is also reduced for communication. So if you remember, in circuit switching we have to wait for our turn, when will the turn will come, and then we will get there to perform the communication. Okay, so in this particular communication, the waitage time is very less. The human intervention is removed. Now the packets are automatically reaching to their receiver with the help of the header. So in the header, the information of the address of the receiver is already there. So that is the main advantage of it. Now, the main question was that how you divide the packets into how much packets. Okay, so divide the communication into how much parts, that is called your packet. Okay, so I've taken an example. In this particular example, firstly I have divided the packet into four. uh, when I divided the packet into four, the total time that I reached with the help of a pipelining is around 1.2 millisecond. Okay, so if you've seen, without the pipelining, the total time was 3.1 millisecond. And if I just increase the packet size, like where we were using 5 packets and now increase the packets to 10, now we have come to the time of 2.4 milliseconds. Okay, so the time here is increased. Okay, so now if I increase the package size to around 20 millisecond, so what will exactly be the time? Okay, so again the same procedure will be there. So that for because you're dividing the packets into dividing the data into 20 packets. Okay, so if you are dividing the data into 20 packets, it means that every packet size will be 50 byte. Okay, so 50 byte of data will be contained in the packet with the header. Okay, so header, you already know, it's of 100 byte. Okay, so one packet size will be 50. If you're seeing here, data size is very less and the packet size is very is more than that data size. Okay, so now again the same approach you have to follow. So one packet size will be 150 byte. And what is the transmission time? So transmission time, you already know, length of the packet over the bandwidth. So length of the packet will become 150 byte over bandwidth is around 1 mbps, I think. Yeah, bandwidth is 1 mbps. It means 10 raised to power 6 bytes per second. Okay, so if you solve it, I think it will be around 0.15 milliseconds. And for one packet you are taking, so again the pipelining formula will be there. So for first packet to get to the end of the receiver, it will take around because it will there on the way there are three transmission times will be there. So if this is your sender and this is your receiver, this is your sender, first transmission time, second transmission time, and third transmission time. Okay, so for the first packet from the sender to reach to the receiver, the time will be 3 into whatever is the transmission time for a packet. Okay, so the for the first packet. Okay, so what is the transmission time? It is 0.15. So 3 into 0.15, it will be 0.45 millisecond. And for the remaining packets, whatever remaining packets are, this is first packet and 19 packets are remaining. So after every 1 tt you begin to get the packet at the receiver end. So it will be 19 into tt, it will be 19 into 0.15, and I think it is 19.5, it is 1.85 millisecond. Okay, so now if you want to find the total time is your tt. Okay, total time will be 0.15 plus 1.85. So I think it will be just wait a second. Yeah, I think it will be 2.3. Okay, so just wait a second. How? Mm, just wait a second. Okay, so I think there is a calculation error here. It is 2.85. Okay, there is a problem. Now 2.85. Now it will become 3.3 because I think because if you see that I have divided the communication into 20 packets, it should not be less than the size of the previous one. Okay, so for 10 packets it was 2.4 milliseconds, and for 20 packets it is around 3.3 milliseconds. If you say the answer without pipelining, I think it's also 3.1 milliseconds. Okay, so if you're dividing the data packet into many packets, so if you're dividing the data into like 20 packets, so again we are getting more time here. Okay, so the time that we require to reach to the sender to the receiver is more than the actual time without using any pipelining. So with the pipelining here is 3.3 millisecond, but without pipelining, if you see, it was 3.1 milliseconds. So okay, so it depends. Okay, so because it is of 20 packets, it is divided into 20 packets, and every packet will contain 100 bytes of data. So this is a 100 byte of header. So actually the size of the data get increased. Okay, so again, for 20 packets, every time for every 20 packets you have to attach this 100 byte of data. So that is why it is very important that you understand it, how much is the optimal time that you, how much is the optimal part that you divide your packets to. Okay, so if you are dividing into so much many packets, it will again take much more time than with the pipelining. Okay, so if you are dividing this packet into like many if you're dividing the communication into many packets, so it will take more time than your pipeline without pipelining. Okay, so the packets, if there is a packet, means that you are able to perform the communication with the pipelining. Okay, so keep that in mind. The packet division should be optimal. So you do not have to divide so it that communication into so many packets, so that it will eventually increase the eventually increase the data of the whole communication. Okay, so that is very important. So that is why in this particular case, I think 5 packet is the if you divide the communication into 5 packets, it is getting the highest result. So I think it is 1.2 millisecond. Okay, so if you divide the packet, if you divide the data into 5 packets, you will only get 1.2 milliseconds with the pipelining, and without pipelining you are getting 3.1 milliseconds. So there is a huge time difference, and because if the data is smaller, okay, so it is only of 1,000 byte. Okay, suppose the data is like million bytes. Okay, so then this particular time has a huge difference. Okay, so that is how your packet switching works. Again, it is divided into two parts. So I'll just let me switch towards the packet switching. So packet switching, all you know, packet and message switching is very similar to each other. I'll tell you the difference also. Now in this packet switching, you only know that there is particular something called store and forward, and the main feature of this packet switching is you can divide the message into smaller packets. Okay, so every packet will contain a header. There are these are 2 or 3 main points that you have to remember. Okay, so every packet has a header. So if you switch the packet, it will eventually reach to its destination because the header contains the address of the receiver machine. Okay, so now it is divided into again two parts. The two parts are your virtual, it is approach of packet switching that is mainly used. It is virtual circuit switching. Okay, so again what they do, because the circuit switching has the advantage that the connection is flawless. Okay, so first, if the connection is established between the sender and the receiver, if you remember, then the there is no problem. So all the communication will be flawless, and there will be no problem any kind. Okay, so that is the advantage of circuit switching. So now this circuit switching advantage we want in packet switching. So what we do, we something another approach is called virtual packet switching. Now it is what exactly happens there. So firstly, at the sender side, you divide the data into smaller parts. You're called that is most preferably called as packets. And these packets, so this particular packet, this is the first packet, it will contain the header. Okay, so only this first packet will contain the header. And when you send the first packet, when you try to send the first packet from a sender to receiver, all of the packet will be following this packet. Okay, so no other packet will contain the header, only the packet that is at the starting of the train. Okay, so it is something like a train that first that packets are following. Okay, so if the first train or the first head of the train is containing the address to which receiver to reach to, and it is something like that, this particular packet has put a rope, and all the packets are putting a rope on the next intermediate packet. So the communication is just it is flawless. It is just following the same approach of circuit switching, but only thing is that the data communication is divided into a form of packets. But in actual circuit switching, what happens, there is no packet division. All the communication is directly transferred from sender to receiver. Okay, so this approach is somewhat like circuit switching, but it also contains the flavor of a packet switching, because it is divided into two parts. Okay, so again, the approach is again it is a connection oriented approach. So if I think it is written, yeah, it is a connection oriented approach like the circuit switching. It means that the a connection will be established first between the sender and the receiver, and then again the route is already pre-planned, all the things. Okay, so call request and call accept packets are used to establish the connection. If you remember in the early days, that if you want to place a voice call, you can request from a particular network ISP, internet service provider, that I want, if you remember in the starting, that a lines to lines call was free in the very beginning. So a network to network call was free, because network to network call is that, because if for a particular company it is very easy, it is very easy to optimize the resources and free a particular set of resources across sender and receiver. It was very easy in the starting. But if the voice call was between inter networks, okay, so suppose it is between Reliance and Geo, so it'll there will be an extra cost that was attached to it. So at that time in the starting, this particular thing, that if you know about interconnect charges, that was there. So in the starting it was there, but now I think interconnect charges are abolished. Now it is abolished by Terai. But actually you understand that what happened was that if you want to communication between the same network provider, it is very easy for the network provider to free the resources between sender and a receiver. So that particular communication was virtual circuit switching. So that is because packet switching is efficient resource, and virtual circuit switches is again making sure that the connection is connection oriented, so they free up the resource. But if you want to perform between various different network providers, that then you have to pay something extra. Okay, so if you remember. Okay, so now there is another approach that is called your datagram packet switching. So datagram packet switching is pure packet switching. Okay, so there are various kinds of packets. The data communication or the message is divided into various packets, and each packet is containing a header. Keep that in mind, each packet is containing a header, and they can follow any path. Okay, so suppose to reach sender and receiver, there are many paths exist. So what they do is, it is that suppose there is a router, another, there was then this one, and then this one, and then it is another one. something this particular path exists. Okay, so what this when it is divided into various parts, so suppose these are the packets, so any packet can follow any path. Okay, so it is a traditional circuit packet switching. Okay, it is what is it. Okay. So now you know packet switching. In datagram packet switching, it is mostly used in your internet. Okay, so most of the internet is based on the datagram packet switching. Okay, so the data is divided into smaller packets, and they are again transmitted across the various networks or across the various network devices. Okay, keep in mind that when you are sending the packet, they will not follow the same order. They may or may not follow the same order. Okay, so if they are divided the packet, this particular message into 1 2 3 4 packets, so it can happen that at the receiver side, the packet received like 4 of 2 1 and 3, something like this. Okay, so it is not mandatory that all the packets will follow the same path. Any packet can follow any path based on the decision of of this router. Okay, so router on the path will decide that for which particular packet, which particular path is good. Okay, so now again keep in mind, in datagram packet switching there is no pre-planned path, there is nothing dedicated link, there is there is every header, there is a header attached to every packet, and mostly the internet, or you are when you are accessing internet, this kind of datagram packet switching is used. Okay, so keep in mind, so when you are doing voice call, most of the time virtual packet switching will be used, and when you're doing internet, when you're accessing internet, most of the time your datagram packet switching will be used. Okay, so another one is your message switching. I'll upload the ppt also on the LMS, so you can refer to this one also. So another one is your message switching. So message switching is again is again very similar to packet switching. Again, it has the feature of store and forward. It can store the message into around different network devices, and it can send the message or put the message onto the link whenever he sees the whenever it sees that the resources are free. Okay, so this technique is somewhere in the middle of circuit switching and packet switching. So why it is called that it is somewhere in between the circuit switching and packet switching, because it has the feature of circuit packet switching of storing and forwarding the message whenever it is received. And why it is in the middle of circuit switching, because it also has the feature, it does not divide the data. Okay, so it does not divide the data into packet, so the message will remain intact. Okay, so that is why this technique is between a circuit switching and a packet switching. In message switching, the whole message is treated as one data unit, and it is switched or transferred in its entirety. Okay, so switch working on message. Okay, so everything will be similar. So the message, keep in mind, the only the advantage of this is that the message is not divided into sub parts. All the message that if you are on the way, so if there is a computer there, so the message will send across the computer, but this particular computer or a particular network device has the capability of storing the message. When it stores the message, it will see if the resources or this link is free. Whenever this link is free, it will again put the message onto the link. Okay, so it does not have that many advantages, because if you know that if the resources or if the link that is connected to between various devices are is very busy, or in this particular link there are many traffic, is there many traffic, you will not find a way to put the particular message onto the link. Okay, so again there are many problems there also, that if you put the message on the link, suppose there is another at that the similar at the same amount of time there is another message coming from the other end of the wire, so you may have not known that, and yeah, a collision will occur and the message will get lost. Okay, so that is why if you want a very reliable communication, circuit switching is preferred. If you want if you want something that your data will that you do not want any manual intervention, as well as your data is divided into parts and it will got reach towards the receiver, you don't mind that how it reaches, then you will prefer a packet switching. So message switching is just a phenomena. Most of the time we will not use message switching. So message switching is rarely used in any concept. Okay, so most of the time you will use your packet switching as well as It is either it is packet switching or it is entirely your circuit switching. Okay, so if you want message switching kind of functionality, you can use virtual circuits, but because of the message switching, you cannot divide the packet, you cannot divide the data into packets. So that is why message switching is not preferred. Okay, so now this is your switching that is completed. So I will upload the PPT. You can refer to it. I will also upload the notes again. You can refer to that one also. So now I'll go there at a very important topic now, because now we are in the uh, actual core computer network part. Okay, so from now on here you will see a lot of what do you say, what do I want to say, that something like these kind of numerical. From now on you will see these kind of numericals and these kind of problems there. Okay, so if you again have any problem, if you understand this particular question of pipelining, I think it is very easy to understand all the things that I will tell you in flow control will not be very tough. But if you are listening to it, if you have any problem, just shout and ask me. Okay, again, if you are watching the lecture at the weekdays or the weekend, just let me know. If you are watching the lecture and you are again facing any kind of doubt, just write a mail to me. I'll try to resolve your doubt. Okay, so now from now on it is a bit I'll not call it very complex because it's very easy, but it is in the form of numerical. Okay, so again I'll try to make it as easy as possible, but still if you have any doubt, just let me know. Okay, so without further going into the flow control, you have to understand what are the various delays. Okay, so delays, I think we have already discussed two delays that are particularly used in CN. Okay, so the first delay is your transmission delay. So transmission delay is the time taken to transmit a packet from a host to the transmission medium is called. Okay, so actual the the language that I used was that the time taken by a host to put the packet onto the link is your transmission delay, but the actual formal definition is this. Okay, so that is why I've taken a PPT to introduce you to the formal definition as well. So it is the same thing, the time taken to transmit a packet from a host to the transmission medium. Okay, so this particular this is your transmission medium. So you know the transmission medium can be wired or can be wireless also, because we have discussed already. Transmission medium can be wired or can be wireless. Most of the time it will be referred to as a link. Link can be wired and wireless. Okay, so again the same example is given there, that if bandwidth is 1 Mbps and what exactly. So to derive out the formula, that B with the bandwidth and L be the bit size of the data, then the transmission delay is TT is length of the packet divided by the bandwidth. Okay, so I already discussed this in quite a bit of detail in when we are discussing in packet switching. So you can refer to that one. Another delay is your propagation delay, that you also know about, that uh, when the last bit of this packet from the last bit of this packet has reached to the receiver. Okay, so the time taken for that particular process is called your propagation delay, or it is most preferably denoted as TP. Okay, so again after the packet is transmitted to the transmission medium, it has to go through the medium to reach the destination. Hence the time taken by the last bit of the packet to reach to the destination. Okay, so last bit is, if there are many bits there, the last bit is this one. The time taken to reach this last bit to the end to the receiver, that time is called your propagation delay. Okay, so again we have already discussed it. There is only only two things involved here. First is how much is the distance that is between the sender and the receiver, and what exactly is the speed. Okay, so what exactly is the speed of the signal. Okay, speed, you already know that the speed will most probably be the speed of the light. Okay, so I'll also discuss the speed that is already default. Okay, so we cannot do anything about the speed that is already fixed, but distance will be varied. Okay, so again distance can be 10 kilometer, 100 kilometer, 1000 kilometer, 1000 kilometer, 1 to 1 lakh kilometer also. Okay, so the speed, the factor affecting the propagation delay is already been discussed, because if you remember, TP is particularly denoted by, because it is a time. So time is distance over speed. So speed here is denoted by velocity here, because in terms of velocity, the direction will also most particularly will be given in your question. Okay, so it is directly proportional to the distance and inversely proportional to the velocity. Okay, so if the velocity of the speed is higher, the packet will be received faster. It's one and the same thing. You can easily understand it. So it's 10th or 11th grade science. Okay, so now the velocity of for air, it is most probably given as 3 into 10 raised to power 10 meter per second, and velocity for optical fiber, it is 2.1 into 10 raised to power. Okay, so it is 10 raised to power, I think, 10 raised to power 8. So 10 raised to power 8 meter per second. So both of the velocity will be given in your question when you are solving. Most of the time it will be air, but if it is optical fiber, this particular thing will be mentioned there, and the speed or velocity will already be given to you at that particular time.
Sir,
Okay.
optical fiber speed won't be faster. It should be faster, right? It should be traveling with the speed of light.
Optical fiber is traveling with the speed of light, but still there is some loss there. So that is why the speed is a little bit lower. Okay. So
Sir,
there is some loss. Yeah.
sir, if optical fiber is slower than air, then why do we use like fiber connection everywhere? Why don't we like just broadcast the signal?
Because in the broadcasting part there will be very many laws. Okay, so if you see a radio signal and another signal, there are many factors attached to that. That is the frequency as well. What is the frequency of the signal? What is the amplitude of the wave? So most of the time the highest resource that you will find is the optical fiber or wired communication is preferred, because uh, it get lost very difficult, and the communication is very reliable. But in particularly wireless mode, you will find various kind of losses that will exist there. So that is why we preferred wired mode. But if you have a long distance communication, you will try to use your wireless medium. Okay.
Okay, sir.
Okay. So now there are another type of delay. There are delay, but they are not used. Okay, so exactly they are not used. Something called a queuing delay. Okay. So now what is a queuing delay? Suppose this is your sender and this is your receiver. Okay. So now what will happen? The packet. Suppose if you have sent different packets from sender to a receiver. Now this is the receiver now received a packet. Now, receiver will always have some kind of a buffer. Keep in mind it because it tries to store the packets that it is receiving from the sender. It will have a buffer. Okay, so the packet will not be processed by the receiver immediately. It will take time because all the packets will be standing here in a queue. Okay, so it will not be automatically processed in one go, but it will take some time, because receiver has a buffer and it has to figure out that which particular packet belong to which particular part of the communication. Okay, so when the receiver is processing, it will go from this packet one by one. Okay, so it will process this packet, then it will process this packet. Okay, so the amount of time for which any packet sit in the buffer, the amount of time for which any packet sit in the buffer and wait before being processed is called queuing delay. Okay, so queuing delay always means time here. Okay, so every packet, suppose this is the packet, the amount of time it will wait for its turn is queuing delay for this packet. Okay, so the amount of time this particular packet wait in the queue is the queuing delay. Okay, so now this particular queuing delay depends upon the receiver machine, that how much time that a particular packet will take it to sort the queue. It will depend upon the processing power and other factors of the receiving of the receiver's machine. So that is why there is no exact formula to calculate the queuing delay. So just keep in mind there is something called a queuing delay, but actually we will not particularly use it. Okay, so many all the time you will, if you are accessing any question or if you're solving any question, most of the time queuing delay will be 0. But if the question in the question that you queuing delay is given there, you can figure it out. Okay, so I'll solve it so that you don't get confused here. Okay, so let the packet is received by a destination. The packet will not be processed by the destination immediately. It has to wait in the queue for something called as buffer, because I already told you the amount of time it waits in a queue before being processed is called queuing delay. Okay, so in general we don't calculate queuing delay because we don't have a formula for that, because every receiver machine is different, and it has various factor that is depending upon the various receiver machine. So we cannot predict that, the sender cannot predict that what actually is going on and what actually is the receiver machine specifications. Okay, so the delay depends upon the factors. If the queue, if the size of the queue is large, the queuing delay will be huge. Okay, so if the buffer is large, the queue, the packets that are in the queue will also be large. So that is why the queuing delay will be large. Okay, if a greater number of packets are arriving in short or no time interval, queuing delay will be large also. So if you think that in the buffer the packets are arriving like after 1 millisecond. Okay, so all the packets are arriving after 1 millisecond. So what will happen, there will be a large queue that will be at the receiver end. Okay, so then it will again take a large amount of time to sort through the queue. Okay, less the number of server links, greater is the queuing delay. Okay, so again, what is the meaning of that? If there are less servers on the way, suppose if there is no router, so there is a dedicated connection between a sender and a receiver, so sender can easily send to the receiver without any interference of any other devices. Okay, so it can directly send the messages from a sender to receiver if there is no other device. So other device has the functionality of store and forward and division of packets. All this functionality is not used if there is no network device on the way. The division of packet, the store and forward functionality will not get used. So all the packets that are going from sender directly will be received by the receiver. Okay, so in that way the queue will also again get large. Okay, so I'll also tell you there are many problems how to sort through the queue, but keep in mind that there is no particular formula for this queuing delay, but you have to know. Okay, and then anyway, another delay is also there, that is called your processing delay. Okay, so processing delay will also again depend upon the receiver machine specification. Okay, receiver's machine. Okay, again there is no formula for that. The processor varies from one machine to another, because when the receiver receives a message from a sender, there are many things it has to do. First it has to check that that data is error free. So for that it has again to have to perform some kind of a calculation on that particular packets, and then it will again depend upon the receiver machine specification. It will take that much amount of time to sort through the processing. Okay, so now the packet will be taken from processing is called processing delay. So suppose this is queuing, and from the queue this particular receiver take up this packet into the processor to find it that it is error free or something is problem, anything that there is a problem in that. So it will be processing through it. Okay, time taken to process, so whatever is the time taken to process this particular packet is the processing delay again. Okay, time taken to process the data packet by the processor, that is time required by the intermediate router to decide where to forward the packet, update TTL, perform header checksum and calculations. Okay, so all the things, these are checksum calculation is used for finding that the packet is error free. All the things that are there is processing. Okay, so again there, if there is intermediate router, it will also divide the packet, it will check that the packet is error free or not. So that is also a processing time that will be required on the way. So that amount of time we will not, again there is no formula for this particular delay. So again, if you are using a router and you are using a very high spec PC, it will depend upon the specification of the device that you are doing, that you are using it to transfer. Okay, so it does not have a formula, since it depends upon the speed of the processor, and the speed of the processors varies from computer to computer. Okay, so only in particular communication we'll try to use a transmission time as well as your propagation time. Okay, so transmission time is the amount of time required to put the packet onto the link, and the propagation time is the time that the final bit or the last bit reaches to the end of the receiver. Okay, so most of the time we will use these two time. However, if you have given in the particular question you are already given with the propagation delay or a queuing delay, you can again use that time, but most of the time it will not be given. If you look out for any Cisco exam, as well as if you look at any gate question or GATE or any other exam, you will not find any question that will contain processing delay as well as your queuing delay. Okay, so most of the time we will be talking about only the transmission time as well as the propagation time. Okay, so this is the delay depends upon the following factor. It depends upon the speed of the processor. So these are the some formula that is given to it, but we actually do not bother about this formula. So total time will always be on the uh, transmission time as well as on the processing time. Okay, so the total time here is like that. It is saying that for a communication, what will be the total time? Okay, so for a communication, so when you send a packet from a sender to a receiver, what will exactly be the total time? First time will be the packet, when you put the packet onto the link, that will be your transmission time, and second time will be your propagation time. Okay, third time will be your queuing delay, but this I do not know about this particular formula. And the fourth time will be your processing delay, that again we do not have formula for that, so we are not considering this. We are only considering these two time for calculating the total time. Okay, so they are again ignoring, or they are saying that this particular time is negligible. Okay, so when taking TQ and T pro, they are equal to 0. Okay, now now we will start with our topic. Now I think you understand all the delays that exist in uh, computer network. Keep in mind, we only try to use transmission delay as well as a propagation delay. Okay, so now go towards the flow control. Okay, so flow control, what is a flow control? If you remember, flow control functionality is in the data link layer. Okay, so data link layer contains first functionality, that is your framing, and second one was your flow control. Now I have already told you that what we are discussing in the OSI layer, or in any data link layer, or any physical or any layer, all these particular things we will be going to discuss in detail. Okay, so another thing was your error control. Okay, so whatever there is a error in flow control, we try to solve this with error control. Okay, so now we will go deep into this particular flow control. Okay, so flow control has two main methods. First one is your the stop and wait. Mostly this will be used, so it is assumed that the channel is noiseless, so it is for ideal communication. Practically it is not used, but it is referred that the communication is ideal, there is no kind of noise going on there. For noisy channel, there is something called sliding window protocols. Okay, so there are three types of sliding window protocol. That is your stop and wait, ARQ. So ARQ means automatic repeat request. Okay, so I'll tell you, we will go deep in every of the protocol that is defined there. Another one is go back and ARQ. I'll tell you about this one as well. Third one is your selective repeat ARQ. Okay, so ARQ means automatic repeat request. Okay, so now before going further into the protocol, so we have to understand that why we use flow control, what is the need of flow control. So what actually is a flow control? Okay, so suppose you are sending a packet from a sender to a receiver. Okay, so there is a simple communication between a sender and receiver. So what happens is that in the receiver there is something called a buffer, you already know. So I've sent 1 2 3 4 packet. Now the buffer here is full. Okay, so the buffer here is full. Now the sender do not know that the buffer is full. Again, it is sending another packets like 5 6 7 8 9 10. But the buffer is full. The receiver will discard everything that is coming to it, because it just does not have the space to accommodate these packets. So it will discard everything. But the sender will not get any signal, any kind of a thing that this particular thing is discarded or something is there. Okay, so flow control mechanism come in place in order to ensure that there is a smooth flow between a sender and a receiver. So for this, a particular example you may have seen is that when the sender send a packet, the receiver send a acknowledgement of the packet, that I have received the packet, and you can send the next packet. Okay, so why every receiver, if you see in your labs as well, they all the receiver when receiving a particular packet, they send the acknowledgement back towards the sender saying that now I am ready, you can send a next packet. Okay, so that is a simple flow control mechanism that avoids any kind of the overloading of the space or the buffer that is already given in the receiver. Okay, so acknowledgement can be sent late also, though if you have many packets in your buffer, you can send the acknowledgement late to the sender saying that I have a little bit amount of time, I require a little amount of time to process the packet that are already in the buffer. Okay, so this is a simple flow control mechanism to in order to establish that there is a simple or smooth flow control between the sender and the receiver. Means that why we need flow control is because to ensure that the receiver receives the packets that is sent by the sender. So we have to maintain a flow between a sender and the receiver such that all the packets that are sent by the sender will be received by the receiver. Okay, so now the simplest flow control method you will find is stop and wait protocol. Okay, so it is the simplest one. So I think you may have already seen it unconsciously or subconsciously, sorry, not unconsciously. If you take a sender and then you are receiver, it is the simplest one. You just send the packet to the sender, you just send the packet to the receiver, and now the sender will stop when one packet is sent to the receiver. The sender will stop and it will wait for the acknowledgement from the receiver. Okay, so when the acknowledgement comes towards the sender, it will again send the next packet and wait for the acknowledgement that will be sent by the receiver. So that is the simplest method. I don't think there is any kind of a problem here, but it is again ideal. It is an ideal situation. Why it's ideal? Because if you see, it's work under the following assumption that communication channel is perfect. So as you know that nothing is perfect, because the communication channel also has a noisy and other things. It can happen that there is a the wire is broken between the sender and receiver. So we are again working under the assumptions that the communication channel is perfect and there is no error occurs during the transmission. So that these two assumptions that we are already assuming. Okay, so this is the simplest method, stop and wait. Okay, so before going on further, I'll just we have to calculate some terms that we again will use further also. Okay, so I'll show you the diagram. It will be that much easier. Again, it's suppose I'll show you how stop and wait works. Okay. Now I am combining all the transmission delays that we have already studied in this stop and wait to find out that how much transmission and propagation time will be required. Okay. So suppose if this is enough, I think it's enough. Okay, so this is a sender side. All the time you will see this kind of a diagrams. Okay, so this is a sender side, this is a receiver side. Okay, so now you are first of all you are sending a packet towards the receiver. Okay, so now you have to put the packet onto the link. Okay, so the amount of time that you will require is transmission time. So whatever it is, I'm just denoting it as transmission time. When you have put the packet onto the link, what you'll do, you will send this packet across the receiver. So this amount of time, you already know that how much this time will be. It is your propagation delay. Okay, so again just wait a sec, I'll send. This is the packet that is received by the receiver. Okay, so first time is your transmission time. Second time is your this particular time, that is propagation time. So propagation time, I'll write like this. Okay, so now this is the sender. Now it has put the link, put the packet onto the link. For that, what exactly is the time required for it? It is tt, and it has waited for this much amount of time. This particular time is the time that the last bit of the packet reaches towards the receiver. So I'm calling this particular time as propagation time. Okay, so again the sender has waited for this amount of time tt, plus it is waiting that the packet will reach to the receiver. Now it will again further wait. Okay, so there will be also queuing time and processing time. but we already ignore that. So just for the sake of simplicity, I'm considering it. Okay, so there will be some time called TQ, that is your queuing time, queuing delay, and then there will be some processing delay. So I'm just, for the sake of including all the times in the calculation, I'm including these two as well. Okay, so it is your queuing delay at the receiver side as well as the processing delay as the at the receiver side. Okay, so after a particular queuing or a processing delay, now you have to send the acknowledgement towards the sender. Now you have to put the acknowledgement onto the link, so it will be T, I'm denoting it as T acknowledgement. Okay, so the transmission time for to put the acknowledgement onto the link from the receiver side, it will take T acknowledgement, and it will again send this particular acknowledgement to the sender here. So this is your acknowledgement. Okay. So now the sender has again waited for this time, TQ time, for the receiver. This is just from the this is the time that is used by the sender. All the other time, for this time it is waiting, for this time it is also waiting, and what will be the propagation delay as well, it will be again waiting. Okay, so what is the propagation delay from this one, from this particular time that the receiver sends the message back to uh, a message back to your sender? This is again this much amount of time the sender will again wait. Okay, until it does not receive the message. Okay, so now this is a simple stop and wait mechanism. Okay, so actually we'll try to find out the total time, that how much time it has taken for a single packet to go across the sender and the receiver. So that is why I've shown you this diagram. It is also given in the next one, so I'll just show you. So it is yeah, this one is this one. It is simple stop and wait protocol. Just wait a second. And this one, I think it, yeah, this one is the diagram of it. Okay, so this is the transmission delay of the packet from the sender side. So it is given at the receiver side here, a transmission delay for the packet, whatever is the time required. So this time, only this time. Okay, second time is the propagation delay of the packet as well. Okay, so whatever is the time required, so this from this particular amount of thing to particular, whatever is that amount of time to reach the packet at the receiver end, this is your propagation delay. And there will be some queuing delay, there will be some processing delay. I don't want to this is exactly zero, but I just don't bother about it. Okay, again there is transmission time to put the packet onto the, to put the acknowledgement onto the link. So that is another transmission time that will be required from the receiver side. And again there will be propagation time from the receiver side, from this to this, from this to this. Okay, so this to this, there will be a propagation delay. Okay, so now there will be a queuing delay and processing delay from the sender side as well. So we will ignore it, we will try to ignore this particular thing. Okay, so actually if I go back to my diagram, this is the diagram, I can copy it. So if I just
So once can you tell what is the difference between transmission and propagation?
okay, so the transmission time is to put the packet onto the link. So this is your transmission time. And propagation time is when the packet from the sender to the receiver, when the last bit of the packet reaches from the sender to the receiver, is the propagation time. Okay, transmission time is to put the packet onto the link, and the packet when goes towards the receiver, that much amount of time is called your propagation delay. Okay,
Okay.
so that is why I'm saying here, if you see, when the sender tries to send the message to the receiver, first of all, it will put the message onto the link. So that is the transmission time that will be required from the sender side. So I'll just write what exactly is the total time that will be required here. Okay. So it is also given in the PPT. Don't worry, I'll get back to it. So now it will be first TT. TT from the sender side. I'm just writing it so you don't get confused, from the sender side, and it is TT for the data. Okay, so first time is that. Now another time will be the propagation delay, that we are sending this packet towards the receiver. Okay, so propagation delay, again I write it, it is for the data, and it is sending from it is sent from the sender side. Okay, so that is why I'm writing a sender. Another time, another time will be that when it reaches to the receiver, it will take queuing delay as well as processing delay. Okay, so these both time are from receiver. This both time is required at the receiver machine. So this we are at here now. Okay, so now the receiver has to send the acknowledgement back to the sender, that we already know. So that again it has to put the acknowledgement onto the link. Okay, so I'll say that transmission time for acknowledgement. Okay, so it will also be there. It is from the receiver side, so I'm writing R for receiver. Now it will again the transmission the propagation, it will again be proper, it will be sent from the receiver to the sender. So again this particular time will also be calculated. This is your propagation delay. Okay, so propagation delay again from the receiver side. Okay, so now these are your total times that will be there. Again from the sender side you can calculate that there will be a queuing delay as well as there will be a propagation delay. So I'm just assuming these as 0 because I have already told you there is no way to find out what exactly be the queuing delay for a particular machine and for a particular sender or a receiver. So I'm just deleting it and I'm renaming as 0. So this will not I'm not counting this time. So this is, I'm saying that it is negligible. Okay, so now go towards it. Now what exactly be the propagation delay? Okay, so now see the propagation delay of the data, because you already know that the propagation delay, all the factors are same. Okay, so the factors here for the propagation delay are just I'll write it from the receiver side, from this is from the sender side, this is sorry, I'll just again write it. So the propagation delay of data, and then there is a propagation delay of acknowledgement. They both will be equal. This is from the sender side, this is from the receiver side. Why they are equal? Because propagation TP depends only two things, that is your distance upon velocity. Okay, so the distance between the sender and receiver will both be same. So if you are sending the packet for to from the sender to the receiver, the time required will be same, as well as if you're sending the acknowledgement for to from the receiver to the sender, the time required will be the same here. Okay, so that is why I'm saying that the propagation time from the sender to the receiver is equal to the propagation time from the receiver to the sender, because the only two factors are involved here. There is a distance. So if there is a distance between 10 kilometers between the both of the sender and receiver, the distance from the sender to receiver is equal to the distance from the receiver to sender. And velocity, we already know that velocity will be fixed. Okay, so velocity will either be the speed of light or either will be the speed of optical cable. Okay, so if these two are equal, I'm just denoting it as 1, so that is my TP. Okay, so now if both are equal, I can say that transmission data, that will be different. So data and acknowledgement has different size as well. So TT of data from the sender side and TT of acknowledgement from the receiver side. I cannot call these as equal because acknowledgement has a different size and data has a different size. So I'm not saying that these are both equal, but I can say that these particular things are equal. That transmission propagation delay from the propagation delay of data and propagation delay of the acknowledgement. Okay, so yeah, this is acknowledgement, propagation delay of the acknowledgement. Okay, so now I will call it 2TP. Okay, so now if you say now in the next step, I will say that the acknowledgement is a very small amount of data. It is like 1 bit. It is not more than 1 bit. It is just 1 bit of data. Okay, so data, this particular data size can be in the form of byte, or it will be numerous data bits. Okay, but the acknowledgement is only of 1 bit. Okay, so that is why the transmission time that to put that TT for the acknowledgement is somewhat negligible. Okay, so the time required to put 1 bit onto the link is very less, such that I am just ignoring this one. So it is just like 0. I'm just assuming that it is very less. So I can calculate this time as 0. So the last time, that your total time will be TT plus 2 into TP. Okay, So till here, if you have any doubt, just ask me. What is the total? If you have any doubt, just ask me. Okay. So I'll discuss everything in the next one because I do not want to leave anything in between. Okay. So you can move on to the next lecture. If you have again any doubt, if by again watching that lecture, if you have any doubt, just ask me on the mail or on the